So once again, welcome back, and this is in continuation of the first lecture on electromagnetic induction, wherein we learned about the experiments of Michael Faraday and Joseph Henry, and later on the explanation given by Lenz, the German physicist Lenz. Difference of about 4 years between the discovery and the plausible explanation for that, and that is putting a minus sign in the expression E is equal to minus d phi b over dt. I'm sorry, the expression was E is equal to d phi b over dt by Faraday, also by Henry, the experimental physicist, and Lenz put a minus sign. Okay, and he became famous for that. Okay, now today, extending that thing, because there what we had, that the changing magnetic field was responsible for the creation of the electromagnetic EMF, and thereby there was a current. I will not call it electromotive force, but they could call it, because at that time it was only known as electromotive force. But today we know it that it is EMF, and that EMF too written as small e, small m, small f together, grouped together, and we don't call it M, we call it EMF for historical reasons. Well, we'll talk about a new mode of changing the magnetic field, the flux due to the magnetic field, and the arrangement is very simple. We have the green lines as they show M, S, R, N. This is a metallic railing made up of such material that the resistance per unit length is negligibly small. Okay. Then over this rails we have a sliding rod PQ, which can move this direction or move this direction, okay, with the uniform velocity or non-uniform velocity. It can be accelerated, it can be decelerated, etc., etc. But right now we'd like to make our life simple. So we have the sliding rod has a resistance which is not equal to 0. It has some resistance associated. Now this X cross and this cross, actually I have shown that there is, in this entire area, there is a magnetic field which goes into the board, okay, everywhere. But I don't want to make it too many crosses made there. I don't care. So this cross is the uniform magnetic field, and then we define, because x is equal to 0, x is equal to x, and in this case we are moving towards left. So the velocity in this case, the speed that we have, the velocity is equal to minus dx upon dt. Okay. And we see that when this rod is brought like this, then the phi b decreases with time t. So there is a change. Okay. How much is phi b? The area, this is x and this is L. So the area of this rectangular area becomes equal to L into x. Okay. So the uniform magnetic field multiplied by Lx field give us the phi b, Elx. So now the induced EMF, including the Lenz effort. So Faraday Lenz law or Faraday-Henry Lenz law says that E is equal to minus dB, d phi b over dt. So B is a constant, L is a constant for a given magnetic field and for a given breadth of this railing into dx dt. Okay. Now minus dx dt is equal to V, so I can write it as BLV. Right? Alternately, we can make use of, I will come back to this again, regarding the direction of the current and the EMF etc. Alternately, using Lorentz force, we can write as to what is the force acting on a charge Q, a plus Q, when it is moving in this direction. I am going to discuss that direction also. But right now, let's get rid of this mathematics part, which is easy. So the work done on charge Q, where it is here, 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 this is a positive charge. And you know that historically, current is the flow of positive charges. So this, on any chart over here, this becomes equal to QVBL. Okay. The work done in moving a charge from P to Q through the length L becomes equal to QVBL. Now EMF is defined as that work done per unit charge. Okay. So this becomes equal to Q and Q cancel out and E becomes equal to VBL. The same as this BLB. But I remember it always as VBL because one of my very dear teachers who taught me for 3 years through the BSc final and my MSc classes at Hindu College, Moradabad, is the grand old man who used to be very dear to me. His name was Vishnu Bihari Lal Malhotra, VBL Malhotra, we used to call him. And so I remember it by VBL. If you want, you can remember it by VBL, otherwise else VLV or LVB or whatever you like. Okay. The only thing is that you should remember. Now one thing before I go for the directions, I must tell you that the Lorentz force is equal to QE plus V cross P. This becomes equal to only QE if the charge is stationary and only this electric field is there. So now this very idea of d phi b or d, okay, this plus other things, they paved the way to understand as to how electricity and magnetism are related. Then about that, I have another story to relate to you. Now Faraday, from his home to Davy's place and from Davy's place to home, used to pass through a bookstore. And there was another old man he used to talk to, and he used to ask if you have any new books, this, that, have you read, can you explain that to me, what is the good book, what is the bad book, this. And this old man Donald, he was also very much interested in the changes that were taking place at that time in electricity and magnetism. So one day, they were talking and the old man said, "Look, Michael, so many people are saying so many things about electricity, about magnetism. Why don't we assimilate, take interviews of these people, collect the material from them and publish in the form of a monograph?" Michael smiled and he said, "Will it be of any purpose if we don't check what they are saying?" He said, "What do you mean?" Michael said, "We must test what people are saying." He said, "Then that requires some experiments to be done to see if what they are saying is correct or not." And he said, "There are coils, there are galvanometers and this and that and wires of different kind that we need to purchase." And this man, he smiled. He said, "Yes, Michael, you are right. The monograph will be of no use if we don't verify it, if we don't do it experimentally. That's science. Do it and verify the results. Then, how much you think that you are going to require?" Michael Faraday, he thought and thought and thought and thought. He said, "Maybe 100 pounds. And the man went inside, opened his iron safe and came out with 50 pounds sterling, and he gave it to Faraday. Said, "Go, have your laboratory." And that is how the 8 square feet to 10 square feet place in Faraday's home became the landmark laboratory in the history of magnetism. And so Faraday in England, he found that there is an intermingling kind of relationship between electricity and magnetism, and basically they are one and the same thing. Gave explanations, etc. So look here. Now, I am going to emphasize again that this is my thappa rule. This is my thappa rule. Left for the negative charge and right for the positive charge. My fingers in the direction of the magnetic field, my thumb in the direction of the motion of the charged particle, and my open palm in the direction of the force that is applied on that. Okay. So let's go here and apply our rule. Interesting. So what happens basically is that when the magnetic field is into the board, okay, into the board, okay, and the current is in this direction, okay, current is the flow of charges, it is in this direction, okay, no, but this is rod is being moved in this direction, okay. So what will happen? The current will flow, the charges will flow from P to Q. What charges? Positive charges. So this end becomes rich in positive charges and this end becomes, there is a paucity of charges. This end becomes positive and this end becomes negative. So the direction of the current flow in the railing is as shown here. As shown here. Okay. This PQ serves as the two ends of a source of EMF, which I have shown here. So what happens? What happens is that the current gets out of the positive and gets into the negative as a natural flow. And here this PQ, so the positive out of the positive into the negative, inside it flows from P to Q like this. Okay, so this is the reason why I have marked the current with red ink to be going like this. Some of the authors and some very renowned set of authors, for this particular case, they show that the current is flowing in the opposite direction. Okay, no problem. Well, so the current is flowing like this, and naturally when the current is flowing like this, and then if I hold, okay, the current which is flowing like this in my right hand, then of course we find that the direction of the current inside is something else. Okay. In the Lorentz force, there is charge plus Q. This is shifted like this. Magnetic field is shown like this. Velocity is shown like this. Okay. So I have again the same way. The charge is traveling from here to here, and this PQ serves as a source of EMF, minus here, plus here, and I'm showing that E coming from the higher potential to the lower potential as was defined earlier. Now, next we are going to take the case of a uniform magnetic field, okay, and it's a very interesting case. And suppose at the center of a circular, there is a circular ring, like the rim of the bicycle, okay, and this is one of the spokes of the bicycle, and this is made to move like this. Okay, so what happens is that between the ring and the center an EMF is developed. How much is the EMF developed? Okay, and how things are happening. As an example, I am extending the motional EMF, which was defined with this help, with the help of that particular problem. Follows. So I now take a famous example, which is taken by all techs, okay, in all coaching centers, etc. Well, it is about the motional EMF generated between this is a metallic ring, just like the rim of a bicycle, and this is the center, and the magnetic field is going inside all over. That could be the Earth's horizontal component, etc., etc. Now, I've just shown to you that this is basically the metallic rod we are talking about, single rod, but this makes an angle theta with this in time t. Okay, t is the time. So there is a rotation of this rod, which is rotated in the anti-clockwise direction. Okay. Now the magnetic field that is taken in one of the texts, famous texts, is my God, is 1 Tesla. Okay, which is a very, very huge amount. They should have taken a practical value. Anyway, since they have taken, so I have taken from there. It doesn't matter. The magnitude doesn't matter. Accordingly, the EMF will be amended. Now, this is also taken from the same book, that the frequency of revolution of the rod on the metallic rim is taken as 50 revolutions per second. Always check it, because sometimes teachers, they put so many revolutions, 120 revolutions per minute. Okay, that has to be converted into per second. Okay. Now the axis of the rotation is hinged at O, like this, okay, which is along the magnetic field, parallel or anti-parallel to it. Okay, can go like this, it can go like this, doesn't matter at all. Okay. So, with that, this is the definition of the question. Okay, question written not as it is, how they describe, but in our own words. Because I told you that half of the question is solved the moment you are able to say the question in your own language and make appropriate diagrams which are schematics. Okay, so I have made this schematic. The radius of this rod, the length of the rod is 1 meter, and the radius over here therefore is also equal to 1 meter. Okay. The relation, because this is a uniform kind of a motion, and therefore theta is equal to omega t, where omega is equal to 2 pi nu, like shown there. Now we can attempt, we have to find out as to what will be the EMF between the center and the ring that is there. This is the question. Now there are two methods. In one method, we just talk about the electrons. Okay, the magnetic field is like this. The magnetic field is like this, and the electrons are moving like this. So what will happen? Because there is a right angle there, then the electrons will be pushed from O to Q, and they will be distributed all over the ring, since the ring is a metallic ring. So the electrons will be distributed. So there will be more electrons over here and less over here. As a result thereof, there will be an EMF that will be generated. Okay, this will become positive, this will become negative. Anyway, so what happens? Electrons on OQ move towards ring, towards Q, and they are distributed all over the ring. So the EMF generated over a length dr, some small length dr of the rod, will be equal to B into V, the same VBL. Okay, B into V into dr, where V is equal to omega. Okay, so I can write now that the EMF will be equal to the summation of all the EMFs or small sectors dr, that is integral from 0 to r, which I have not written. And if you don't like, then I can write, but I will not write. Okay, so dE is equal to BVDR. I write it here, 0 to r, BVDR. Okay, 0 to r. Now V I write omega r dr. Right? So B omega is a constant, it's not varying, but r is a variable. So I write 0 to r, r dr, which will turn out to be equal to r square by small r square by 2 between the limits small r square by 2 between the limits 0 and r. Okay, so it will turn out to be equal to, like shown here, B omega r square by 2, and then I substitute the values. 1 Tesla, 2 pi into 50, that is the value of omega, into r square is 1 square by 2, 2 and 2 cancel, so it's 50 pi, and 50 pi is 157 volts, big value. Okay, if instead of Being in Tesla, this were in Gauss, then the value will be much less, reasonable value. Anyway, then we go for the second method, where what we do is that we have a connection between O and P through a resistor, very small resistor R0. Now, this rod is moved from here to there, and there is an area, okay, this area between O, P, Q, O, okay, O, P, Q, O. This area, actually the angle is theta, and theta expressed in radians gives you theta upon 2 pi, and then this area of the whole circle is equal to pi r square. So this turns out to be equal to pi and pi cancel, half theta square, r square into theta. Okay. So now we go to our friends Faraday, and of course we are not taking that minus sign into consideration because we have to only calculate the value of EMF. So we are taking the liberty to just avoid that negative sign. Could do, okay, but it requires a lot of practice on your part. So this is d phi b over dt, ddt of half r square theta, okay, half r square into b, we take out d theta over dt, this is equal to omega. So this turns out to be equal to r square b omega by 2. Connect r square b omega by 2. Okay. Then we substitute the values and we get the same result. So there are two ways to get the result. Now you may ask, and sometimes there is a question, that instead of a single poke, let the bicycle have umpteen, a large number of pokes, and let them be rotated. The rotation takes place. What will happen to the EMF? Now all these pokes, all these rods, all these sources of EMF, they are in parallel to each other. And when we have parallel sources parallel to each other, then of course the net EMF is the same as the EMF for a single rod. So it does not matter whether we have a single rod or we have a large number 2 or 3 or 4 or 5 or any number, like in case of bicycles. The EMF which is generated when the bicycle is moving, okay, in a uniform magnetic field, okay, in that case the EMF generated is given by this r square b omega upon 2 or b omega r square upon 2 or whatever you want to write, and we are able to solve such a problem. So I stop here, and we will in the next outing talk about the energy and power considerations that are there when the EMF is generated by one means or the other means, etc. And remember, you can say that when I am taking the magnet, the first experiment, magnet towards the coil, and the current flows. If the current flows, then there is a resistance in the loop. So there will be I square R heating, which is called Joule's heating. What will happen? That the work that I do in order to take the rod towards the coil, that work done or the rate of doing work, that power is spent by me or you or any one of you, that is dissipated in the form of energy, and that is the energy from the coil. Many more aspects can be done, and we'll talk about that in the next outing. So thank you very much for being with me. Thank you.